sort of a loose spiral structure, but you still see spiral arms, right?
I like that.
Isn't that pretty?
That's gorgeous.
Beautiful.
Love that
Yes.
one.
Yeah, this is beautiful. You can see a lot of detail in there, a lot of star forming regions, which are the red things.
Mm-hmm.
You know,
the color contrast in the spirals. I love it.
Mm-hmm.
Yeah,
nature has the best palette of any artist,
doesn't it?
Yeah.
And this is what's called a face-on galaxy. We're basically looking down on top of it, flat at us like this. You know, so but then we have galaxies like this, where we're almost looking at it edge on. This is known as NGC 4565, a very romantic name, but
also known as the Needle Galaxy.
The Needle Galaxy.
Right? I was going to say, I remembered one called the Needle, and I was wondering if that was it. It does. That's an accurate name.
You're exactly right.
Yeah.
I remember that when we showed this the other night, a couple of our viewers, Daisy and Zoe Amethyst, in fact, said,
"Oh, they're here."
Yeah. Are they here? Oh, hi, Daisy and Zoe. They said it looks like a needle. So they got it.
It's like one of the gazillion space objects I can actually visualize. Oh, needle. Yeah. Okay, I get it. I see why they named it that.
Yeah.
As opposed to everything else that I can't see.
Well, most of us can't see them. Yeah.
Yeah, but you'll notice what makes this thing unique, not somewhat unique, is this large dark lane we call. These are dark lanes.
I don't know what the hell
and these are what these dark.
But YouTube stopped working. Everything else was working. I had to force stop all the streams and reboot and start it all over again. Now I don't know what the heck just happened, but it was YouTube. I had to stop all the streams. That's what happened. It was bizarre. And we're really approaching the time where we have to pay attention. So I'm going to continue with this show.
Globs of dust that you saw here. You see this black dust, this dust in the galaxy. Right off the center of the nucleus, you can see in the spiral arms, they're delineated by the blue stars and the dark dust. Well, from the edge, that stuff kind of looks like this. Now, obviously, this is not the same galaxy, but this is another galaxy that has spiral arms, but we're seeing it almost on edge. We're seeing it a little bit from below. And in the center of this galaxy may very well be a supermassive black hole. And then every galaxy has a different look to us at times. I mean, this one has a special name. It's called the Black Eye Galaxy. And this galaxy we imaged a couple weeks back, actually. And every time I look at galaxies, no matter where they are, I can't help but think that there's a civilization looking back at us. There's got to be someone looking at our Milky Way from there. That's my theory, right?
That's cool.
But I think it's a good thing to think about because it'll keep you sane when it comes to how many possibilities there are out there. And then for our closest galaxy to us, we have this beauty. This is, of course, the Andromeda Galaxy. And you can see the dark dust lanes in that one as well. If this was on edge, it might look more like this guy, but bigger in our sky, you know? And so in the center of this galaxy, there might be, as before, a gigantic supermassive black hole. Now, these spiral arms you see in these galaxies, I mean, there's some new theories about how and why the spiral arms form within the galaxies. And I mentioned before, and a number of times actually, that when a galaxy rotates, it seems like the galaxy is rotating almost like a rigid disk. And when I say almost, that's kind of important. The almost is the important caveat. It's not quite a rigid disk. So there is a differential rotation, a rotation where the outer stars are slightly slower than the inner stars, but not nearly what they should be if we're looking at orbital physics the way it should be applied. It looks like the outer stars are going slower, but not slow enough for that to be the case. So we get these long, drawn-out strands of stars that end up getting, I guess you might want to say, I don't want to say wound up, but they get drawn out into these extended spiral arms that sweep back, right? And that's kind of one theory as to how the spiral arms might form, because we get a burst of star formation and then differential rotation does the rest of the work and stretches the arms out. in a spiral pattern as the stars and the galaxy orbits and rotates. Another details how a density wave theory could play a big role in creating spiral arms. The Whirlpool galaxy, in fact, is thought to not have had spiral arms at all until the interaction with another galaxy that you see in all the photos of it. And that interaction may have caused a density wave, or let's put it this way, a wave of energy that went through that galaxy like a ripple. And that could have started the separation process and started this differential rotation and caused this density of spiral arms that we see in this particular galaxy. Now, how that all works is really pretty elaborate, but the easiest way to imagine what a density wave is by thinking of a helicopter looking down at a rush hour traffic. All the cars are moving in a relatively regular pace until they all start to slow down because they get to a traffic jam, right? There's a traffic jam where there's a bunch of exits maybe, and so those cars all slow down. So let's say they're all silver cars, and one of them's a red car. The red car you'll see slows down, gets into the traffic jam, slowly moves through the traffic jam, and then speeds up again when it gets out of the traffic jam eventually. All right? That's how stars orbit galaxies. They get caught up in this traffic jam of other stars, gas and dust in the galaxy, and eventually work their way free and continue on their way. So it's not the same stars in a spiral arm all the time. How's that for confusing you? But the spiral arms, though, are these concentrations that were induced by a passing galaxy or whatever, and then differential rotation, where the outer parts are a little bit slower than the inner, start to drag these out into spiral structures. We see this all over the universe, and the oddest ones are the ones that have no spiral arms at all. They're just big spheres or elongated spheres of stars with almost no gas. It's just those are called ellipticals. Very strange.
Like M87.
Yeah, and that's actually one of the targets we're going to talk about tonight. So either way, the spiral shape is a natural result of that differential rotation. Okay, and even though galaxies spin like these semi-rigid disks, as we mentioned, there's enough of that difference in their orbital rates that those spirals can be drawn out in these beautiful spiral arcs. And we've noticed, as Daryl has pointed out on numerous streams, some of these spiral arms have real interesting crooks in their arms, as if they had some type of interaction that bent the arm. Right?
Broken.
That's right. Broken arms.
Mm-hmm. Poor galaxies.
Yeah.
And we got a lovely little thank you message for Tara.
Aw, thank you, Vera. That's
Vera,
awesome.
thanks you for saving your stream. And we were just talking about that earlier. Tara is Wonder Woman. Exactly. You called it, Vera.
Yeah.
You guys are too kind.
I think Vera got it right. Yeah, absolutely. So now, when we talk about, actually, I'm going to go on to something next, unless you had something you wanted to add, Daryl.
Can you put up NDC 4565 again for a second?
Sure.
Just rolls off the tongue, doesn't it?
Yeah, there it is.
The needle. Mark, are you in Photoshop? Could you possibly rotate that clockwise 90 degrees?
This is just an image. It's I don't have Photoshop running.
All right. Well, folks, I want you to put your imagination hats on and look at that image for a moment. If you see the nucleus of the galaxy there, the brightest part in the middle, and we turn that galaxy 90 degrees clockwise, so that left lower arm is now the left upper arm. If you projected that up on the ceiling, that is very much what we would see when we look up in the sky at night and see our Milky Way. Our southern horizon is pretty much just to the right of the nucleus of the galaxy, and what's to the upper right below that, above that, but below it to our point of view, that's down in the southern sky. And what we see in the northern sky is that nucleus of the galaxy above the southern horizon, and then that's that arm going to the left, and that dark lane, we see very much the same thing in our sky.
Well, can I
cool.
just mention that I was prepared. I was prepared for you to say that without knowing you were going to, because if you didn't say something similar, I was going to. Because the next photo I have is this one,
Okay.
and there you go. This is a photo taken, believe it or not, at the observatory site just after sunset. You can see the orange of the sunset still there on the right side, and we have the full Milky Way visible to us like this. This is at sunset, guys. That's how dark it is.
Is the
It's
horse
amazing.
in that?
It is. The dark horse is.
Yes.
The dark horse is just below.
Yeah, the dark
center
horse
to
is
the
there.
right.
If you look close, can we zoom in on that possibly?
No, we can't. This is just an overlay. I can't.
Okay. There's a cloud there, a dark cloud shaped like a pipe, like you smoke a pipe, you know? That's called the Pipe Nebula. And that is the horse's back leg. His head is to the upper left of that, and his front leg's a little dimmer. Maybe you'll see the shape of a horse there. And actually, when you look at the bowl of the pipe, the brightest part of the Milky Way you see just to the left of that. That's the center of the galaxy right there. That's where
That's right.
that's where Sagittarius A star is.
Right. Sagittarius A
Cool.
star is what they call the black hole at the
Yeah.
center of our galaxy.
Wow.
So now, speaking, thanks, Genghis and Marco. Speaking of the black hole at the center of our galaxy, we, as I said, we always thought they were there. We always had an idea that they were there, and there's reason why we didn't just imagine these things, okay? Because when we looked at experimental data, I'd like to show you what we saw. All right. So what I'm going to do is I'm going to bring up this guy right here and get rid of this guy right here. Okay. This is this particular study started in 1992. 92. Okay. Some of you listening to this were probably born back then. And this study started in 92. These are all stars that you're seeing, and that plus sign indicates the center of our galaxy. Watch as they look at where the stars change over time and how their orbits change. You can see that the stars are orbiting something in the middle of this galaxy, right in the middle of our galaxy. Let's zoom in there. Now watch. We're going to watch stars come around and orbit something invisible. And then this one, whips right around. So that's the orbit it has. Now, this star, when it gets close to this part here, this is the location where it's closest to the black hole in the middle of our galaxy, or I should say the invisible thing that it's orbiting, is about 120 astronomical units from that. And if you notice, if we actually kind of back this up a little bit, all right, from about here, this was 2001 to about here, 2002. It was about a year to a year and a half that it actually took it to go by the black hole at the middle of our galaxy. Okay, just about a year and a half. So that what we're seeing right there is an unbelievable image, a video that shows what happens at the center of our galaxy. These stars are orbiting something there, and we figured it's got to be a black hole. It's a very, very massive object with a lot of gravity, but it's not something that we can actually visualize, because the black hole is, well, black. We see radio waves, we see gamma rays, we see other energy coming from it, but it's nothing in the visible spectrum.
And that
So-
120 astronomical units, that's 120 times the distance from the Earth to the Sun. So that really, in the big scheme of things, that's not very far at all.
Yeah, well, if you're going by a massive black hole, that's true. This black hole is pretty large, but you say, well, how large is it? Well, I can tell you. Okay, so let's do that. Let's come out of here and let me bring this down and talk about that. This black hole that we saw is this black hole. This is the supermassive black hole at the center of our galaxy. It's called a variety of names. It's called SAG-A, Sagittarius A star. It's not a star. And so when they say A star, they mean the asterisk after the designation. But it's confusing for people to hear it because they think it's a star. It's not a star. It's a black hole. So, but that's all there is to that. And every single black hole we look at looks like a kind of a weird donut, and that weird donut shape is for a very, very important reason, which I'll tell you in a minute. But just by way of comparison, and Daryl, jump in here because I know you have a few things to say. Let's take a look at both of these. Okay, this is Sagittarius A on the right, and this is in our galaxy, 27,600 light years from us. And this is Messier 87, 55 million light years away, but a much larger black hole. And for a size comparison, this is the size comparison. All right. You'll notice that the orbit of Mercury on the right, that's the size of Sagittarius A. Overall that we're seeing there is that it's within the orbit of Mercury. It's not that big. But on the left, you can see Messier 87 in Virgo, and you can see that Pluto's orbit is that small circle labeled Pluto's orbit, and the black hole is several times the size of our solar system. That's huge. That's huge.
I had a question for the video. I think our audience really enjoyed that video. I know I did. In the top right corner, it said 10 light days. What is that in reference to? Is that how far away they were looking, or?
That's just the scale of distance at the center of the galaxy.
Yeah, where were you talking from when we're looking at?
When you had the video on the left, it was counting from 92 to whatever. See, it says 10 light days. What is that in reference to?
That's actually a distance. That's the distance light travels in 10 days visually on the screen. It's showing you that.
Yeah, you could say that's about 1/36th of a light year.
Yeah. So if we're looking
trying to wrap my head around that still. Yeah. I'm sure our audience gets this, but
well, okay, I'll give you an idea. Okay. How far is the sun? It's 93 million miles, right? It's the astronomical unit. But it's 8 light minutes away.
Yeah.
Because it's that close. But if you can imagine, you could go to a certain point where you'll be 10 light days.
Okay. That's what I was wondering. So, but is that counting from Earth or from the black hole?
That's counting this image. It's showing you on this image how far light travels in 10 days on this image.
From Earth.
At the distance of the Sagittarius A star.
Right.
At the distance of the center of the galaxy.
Just the images themselves, the movement of the images to start over is 10 light days.
That's at the distance of 27,000 light years.
Right. 27,600 light years. And at that distance, okay, this at this distance, this magnification, this particular video, as I said, in this image, this is how far light would travel in 10 days. And that's the scale. That's basically like a scale. The scale of this image that's 10 light days in size, basically. All right. And then as it zooms in, that gets bigger because we're zooming in on that location. So that scale gets much larger.
Like I get that we're zooming in, and I get that we're watching this for years and years.
Yes.
But I mean, I'm not going to take up too much time because I'm sure everyone gets this. I'll save this for later on. But
okay, let's put it this way.
Is this just like a computer program, like our best estimate? Because we don't have something at the center, like at the center of the black hole, to be measuring 10 light days away to be filming this. You know what I mean? Like, I'm not. I
understand where you're going, but let me explain. When you're looking at the black hole and you're looking at this star, okay?
From where?
From here, this image, this particular zoomed level, okay? This star, okay, and say this star, let's for argument's sake say that they're the same distance away from us. But how far are they from each other? Well, if this star's light is, say, let's say it's 5 astronomical units away, it would take 5 times 8 minutes for its light to reach this star. So this would be a 40-minute light travel time. But if you could make this star farther away and farther away, then you could see how you could be 1 light day away from this star, for instance. And so basically measuring how fast it would take light, no matter where it's being emitted from, to go on an image, for this to be a scale of 10 light days means that this is how far it takes light to go in 10 days. 10 days meaning if this star emitted light, it'd be over here 10 days later.
If you could imagine, again, when that star was closest to Sagittarius A star down at the bottom of the ellipse.
I'll make that happen.
And you said that was 120 astronomical units.
That's right.
Well, an astronomical unit is 93 million miles times 120. So you're talking, I don't have my calculator in front of me, but
it's 120 times 8 minutes.
Yeah, 120 times 8 minutes.
Right.
And
It'll be
that distance is a fraction of what that 10 light days is up at the top.
Right. So it would take, it would basically be, it'd be a small number. It wouldn't be 10 light days, but it would actually be a much smaller number, because if you say, like, if it's 120 astronomical units and it takes 8 minutes per astronomical unit, 8 times 120, right? Is that 1160?
I'll take your word for it.
Okay, so it'd be about let's round it up, say 1,000 minutes light time. All right, and when it's far enough away,
960.
Okay, so when it's far enough away, it's going to be maybe 5 light days or 8 light days away, and it's farthest, because that's how long it would take light from the star to reach the black hole. So that's showing you basically the scale of this zoom. All right, we're able to see something down to just a few light days across, and that's pretty good. That's why this is such a monumental video, taken for like a dozen years to get this. So I think when you look at this, this points out to me the strangeness that are black holes. Now you'll say that, wait a minute, this star here, it just seems to be going by it. What's going on with that? How come it didn't get stuck with it? Well, probably because of the fact that this star might be either way closer to us or way further away. So it's not as close to the black hole. So it's just wandering by the field. It's not wandering by the black hole per se. All right.
Yeah, it's a line of sight thing.
It's a line of sight thing. Yep. That's right. So that's just a cool video. And let's just watch this from this point of view. Now, some people have said, well, when this star comes through, you'll say, wow, it goes whipping around so fast. Any planets it had must have been whipped away and taken off. Well, let's suppose it did have planets. Okay, for argument, it took 1.5 years for the star to go by the black hole. Yes, it accelerated. Yes, it went fast when it went by the black hole. But it still was maintaining its planets. If it had planets, they still would have been going around. They wouldn't have known any different. They wouldn't have suddenly felt, oh, we're accelerating. They wouldn't feel that, because it would be very gradual. Then the entire system would be accelerating. So you wouldn't necessarily know that you were accelerating, just like you don't feel you're accelerating now, but you are. All right. So the point being that this may not have been a big destroyer. And the other thing too about our black hole is that it's really not growing anymore. They grow when they absorb material. Now, there might have been a point in the recent past where a passing dust cloud was absorbed by the black hole. And yes, it would grow a little bit from that. But our black hole is kind of being starved, in fact. And that's what astrophysics people have been saying. It's sort of starved of material. It hasn't had a whole lot going on.
Yeah.
So it's there. And the thing is, over time, if you keep starving a black hole, well, it's going to evaporate.
They
And-
made a point during the ESO news conference about Sagittarius Star that if our black hole, Sagittarius Star, was a person and you fed that person a grain of rice, you wouldn't feed them again for 1,000,000 years. By comparison, I think is how they said it.
That's a good analogy.
When we look at M87 by comparison, though, M87 is huge. M87 is eating a ton of rice. Put it that way. It's really wolfing it down, but it's so big it moves slowly.
And that's M87 on the left that you can see in this image. And again, notice Pluto's orbit, that little circle. You can put Pluto's orbit multiple times across the center of this object. Now you notice they both look like donuts. And you also notice that they look approximately the same size, left and right. Well, that's because the M87 is about 1,500 times more massive, 2,000 times further away than Sagittarius A. But Sagittarius A is also that much closer to us. So it looks bigger in the sky, and it just happens to be approximately the same size. But you look at the shape. Why do they look like donuts? That's the thing that's interesting. And that's the thing that I'm going to mention and mention to you right now, because I have a little toy that I made for you. I made a black hole to show you tonight.
Cool.
Okay. This is the accretion disk, the disk of material around the black hole, the thing that you saw in orange. I painted it orange just because it was the color they show. Here's my black hole. It's actually a copper ball. And if you know, these are rotating now. The black hole is rotating. The material is rotating around the black hole. But this accretion disk is like the disk of the solar system, like the disk of the galaxy. Disks are a common thing in the universe. They actually occur naturally. Accretion disks form. Toy time with Mark. Yes. Okay. Yes. Yay, toys. They occur naturally in the universe. And let me show you what happens. This is the black hole. It's actually extremely gravitationally strong, right? Obviously, it has a very, very high gravitational field. We know that gravitational fields bend space. What? What does that mean? Well, I will show you. Let's imagine that you have a car driving on a hill. Okay, the car follows the contour of the hill, goes up the hill, down the hill, up the hill, down the hill. Why is it doing that? Why is it just going straight? It's not going straight because the hill goes up and the car is constrained to follow the road. It's constrained to follow all the curves, go up and down. Okay. In the same way, light is constrained to follow the universal path laid out for it by the fabric of space. Light follows the curve of space. So, space-time, that's right. So, when you have a disk like this rotating around a black hole, and here's the far side is over here. You can't see it, but here it is. Okay. You can't see it, but the light's going in all directions. It's going out from the accretion disk. Energy of all kinds is going out toward you, going up, going down, everything. But the light that goes up from the accretion disk is being bent around because it's following the deep curves caused by the black hole sucking, the fabric of space into a very, very deep curve. And so what happens is the far side light from this far side looks like this to your eye. See that? It looks like this because of the fact that the light rays go up and then get bent toward you, because they're curving right around the top of this very, very steeply bent space near the black hole. But you can see them because they're not getting to the event horizon. This is the point of no return. They're just above it. So you see this material. So this is why black holes look like this to you.
Yep.
You saw this in Interstellar. And, Kip Thorne, I had the pleasure of sitting with Kip Thorne for hours talking about black holes, in fact. And this particular shape is something that is predicted by relativity. And we found this shape exactly as predicted when we looked at Messier 87. And now we're finding that shape exactly with Sagittarius A. And so I can say it's as expected.
Yep.
But that's it right
and
there.
If you put M87 and Sagittarius Star both up again, This is why, and I think the ESO scientists were a little nervous about this during the press conference, that as long as they keep using the same techniques, every black hole we look at is going to look like every other black hole
That's right.
in general. Now, Sagittarius star on the right there looks different in detail, but in general, you look at it and what you see is an orange donut.
Yeah, and you see those bright spots, and people say, well, how come Messier 87 on the left has sort of a ring around the bottom here, and Sagittarius A has these hot spots? Why the 3 hot spots? Does that mean they're different black holes? Well, certainly they're different actual black holes, but the processes that they're going through are the same. But the different, there you go. That's, I think, what Charles is asking. Why are there lobes? I'm going to talk about that. Okay, first, let's look at Messier 87. On the left, you see that bright ring? Okay, that's a Doppler shifted value. That's the part of the accretion disk, okay, that's doing this. I'm going to show you right here. I'm going to bring this up. Okay, that's the part of the disk. Thanks, Amanda. That's the part of the disk that's actually coming toward us as this is spinning. Remember I told you it's spinning? As it's spinning, all right, the material that's coming toward us is shifted a little bit into the higher end of the spectrum, a little toward the bluer end, not into the blue, but toward the bluer end. So it's higher energy. So it looks brighter on the radio spectrum that we look at. All right. So that's why we're seeing these lobes down here that are brighter. And when we see the curve, again, the curve is due to the fact that space is bent and the light that's going up is bent over the top because it's following the curve of space. All right. So going back, yeah.
Well, there is a question. I think it's a great question from Uberku. Would that red ring be spherical surrounding the black hole in reality?
It's an accretion disk. It's a plane.
Yeah,
as Mark just said, the light is being bent over and around the top of the black hole, so we see it like that.
Yeah. Now we have an additional problem, and this goes to Charles' question about the black hole. In fact, let's just look at Sagittarius A right now. The additional problem we have is that this particular telescope that captured this is called the Event Horizon Telescope. Now, the Event Horizon Telescope it consists of a number of telescopes around the world. In fact, this is what it looks like. There's 8 telescopes, counting the South Polar Telescope. That's okay, Uberku. I'm glad you asked. All right, that's counting the South Polar Telescope as well, and the telescope in Chile, the United States, Mexico, Hawaii, and Europe. And as the Earth rotates, they each get different observations with these big radio telescopes, and then they're coordinated, normalized, and aligned with each other to make one big 8,000 mile diameter telescope. 8,000 mile diameter is the diameter of the Earth. Now, to see this a little better, okay, let me show you how that looks. All right, this right here is the actual, this guy right here. This is the actual size of this, the Earth, as you can see, 8,000 miles across. But then we actually see this. Now we see this data. This lines connect one telescope to another. So watch now. All right, as we move the Earth, as the Earth rotates. Now these 2 telescopes on the left of the screen come into view and start capturing data. Meanwhile, the one in the upper right drops off in a moment, okay? And now you're just left with these. Now, what happens is these are all taking data, and the data looks like this. This stuff on the right here in this circle. The red dots indicate data points. Taken together, this is 8,000 mile diameter measurements. Now, it's not a full-blown measurement. Obviously, it's crude, but it's good enough that we can actually see what's going on. Now, consider, and we'll watch this again, consider also that when we watch this, you're looking at 8 data points, 8 telescopes capturing data for a certain period of time. And that certain period of time is a few hours each. You got to understand, black holes are faint. They're not bright. So it's going to take a long time to actually capture this data. All right. So they're doing this. They're capturing this data. And as they do that, the data is being sent down to a central location where it then becomes coordinated and normalized for the curve of the Earth, the time at which and most importantly, the time at which the signals get to each telescope.
Yes.
Now, that's important because if we look here, this telescope here gets the data first. This telescope gets the data second. But here's the Earth. Now, if the data is coming from out here somewhere, okay, it hits this one first and it hits this one second. Okay, and it doesn't hit this one at all. It sees different data, as does this one, as does the Hawaiian telescope see different data. All right. So in that time, which is several hours, in that time, what happens is that we watch the data change. And when we look at Sagittarius A here, this image here is blurry. It's blurry because we have so much changing over the time it took to make these observations.
Yeah.
And so every hot spot is dragged out, every detail is fuzzed out. So we can't get a really sharp and crystal clear image like the little toy that I showed you, like the little prop I showed you.
Yes. The ESO scientists made the point that this is what they called a smoothed image.
Yeah.
This is an average of a lot of different images. This is where the scales of the two different black holes come into effect. That Sag A star is so much smaller than M87's black hole that we see things move around Sagittarius A star in a matter of minutes or hours, while M87 is so much bigger, it takes us days or weeks to see much motion.
Yeah,
Just
it's like
'cause it's so darn big.
Yeah, it just takes an hour for material to go around Sagittarius A roughly, and it takes like approximately 2 weeks for data to go around Messier 87.
Yeah, if the video was out there, you'd have to look for it. They showed this during the ESO news conference of like snapshots from instant to instant of what was going around Sag A star, and it's really fascinating to watch. It's very sharp and it's very streaky. One point to be made too, though, is that these are from radio telescopes. They are not photographs. They're not images as we come to expect them or understand them, with conventional instrumentation. They're radio images. Back in the day, Mark, I'm sure, remembers radio telescope images were just colored blobs. They didn't really look like anything.
That's right. Yeah, they were actually colored with primary colors. You actually had red, green, blue imagery, orange, and yellow, and they kind of were graded. And I actually built a radio telescope, and it consisted of a truss work of wooden poles with fine wires strung between them. These fine wires were very sensitive to the resonance created by Jupiter's moon Io, the closest moon to Jupiter, and we could observe the torus of elements that surround Jupiter that are shed from Io as it goes around Jupiter. We could actually observe that torus using this technique, and we had with graphs. We didn't have it was like sodium, I think it was.
Yeah, sodium.
Yeah. And that's interesting too. And we'll get to we'll talk about Io someday, but here's something to keep in mind. Io has an extremely tenuous atmosphere, just an aside here. So let me go over here because it's sort of an aside, okay? So an aside over here. Io's atmosphere is very tenuous. So what happens is on the night side, the atmosphere fully rains out and ends up on the ground as frost, okay? Frost of the sodium ions and sodium material that's the atmospheric components, including sulfur. And then when it comes around the day side, that stuff melts and goes back up to form a tenuous atmosphere. So by night, Io's atmosphere is gone, and by day, Io's atmosphere is back. Isn't that crazy?
That, you know what? I have a perfect analogy.
Yeah.
We'll go to break and disappear, but then we'll be back in about 3 minutes.
Very good, Amanda. I love that. Thank you for that absolutely brilliant segue.
It's what I do.
It's what you do.
Okay.
All right, folks. Well, as she says, we've got to listen to her. She's Commanda. See, it says right there, Commanda. Commander. You got to listen to Commander. We'll be back right after these messages. Don't go away. There's a lot more.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Scrolling all day, time can disappear. Wanna make it count? Why not volunteer?
Posting pics of your food, that takes up time. Time, you've got time to binge all of season 9, though it got so bad.
Time, you got time. We're gonna grow back and be the same browse you had.
Just a few hours to keep families from harm. Help us end home fires, but sound the alarm.
Volunteer for a day to install free smoke alarms in your community.
Discover the Observation Deck, a one-of-a-kind virtual event platform that takes video conferencing to the next level by using avatars to navigate a campus. There's so many areas and activities to choose from. There's a 1,000-seat auditorium, an expo hall, a nightclub, and even a beach. So come attend a conference, take a class, or hear a lecture on the incredible Observation Deck campus. Go to theobservationdk.com.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Anyway, so where were we? Oh, yes. We were talking about the black hole and the reasons why Sagittarius A and M87's black hole look sort of the same. And we talked about some of these other, some of the other information that the scientists had given that Daryl had mentioned to us earlier. And you now know about the shape and why it looks like this, because the light rays going up are bent by this steep gravitational field over the top of the black hole. And so everywhere you look at it from, it's going to look like this. Everywhere you look at it from. It's
every black hole is going to look like that.
Every black hole is going to look this way. They might be bigger, they might be smaller. And depending on how far away they are, it might be sharper or it might be more blurry. Mm-hmm. So
I have a question to that, if I could.
Yes, you may.
Please. Well, so there's an accretion disk on the black hole. So we're seeing it like you showed the galaxies kind of edge on, and then you see the disk kind of flipping up behind it. What if the galaxy is facing us at a different angle like this? Do you see a solid donut type of thing, or how can they all look the same if they're oriented to us differently, I guess?
And they will look very different from a certain point of view. However, let me see if I can do this. Okay. From this position, you'll still get a donut. From this position, you'll still get a donut. From this position, you'll still get a donut because this material is going to go up. This is going to be Doppler shifted, And it's not like it's totally flat. There is some thickness to it. So it's going to go around the middle of that black hole. All right. And don't forget that if you're going to be like this, you're going to have some that's going down, some light rays that are going down the bottom are going to be shifted towards you. And some light rays from the top are going to be shifted towards you. So no matter what side you're looking from, you've got light being shifted towards you from that steep gravitational field everywhere on this object. So no matter where you look at it.
Per Tara's question, and I don't remember the details of how they figured this out, but we know, they said M87 and Sag Star have different orientations, that we're looking at different angles.
About 50 degrees for this one.
Yes.
For Sag, something like this. It's about like that. Like that.
Uh-huh. And if I remember right, M87, I think we were seeing it closer to edge on. And of course, we know the orientation of the plasma jets coming out of it too, which are pretty good indicators of how it's tilted.
Yeah. Like, keep in mind that when he says plasma jets, when a black hole has an accretion disk, those plasma jets are going to be going up and down from the north and south poles of that black hole. And that particular orientation gives us big clues as to how things are shaped and arranged. So when we look at, for instance, this one here on the left of M87, wherever its jet is located, we know that the North Pole is in that rough direction. And then based on an analysis of the...
All right. I've been out there looking. It is super hazy. What the hell is that sound?
Howard.
Could be the air conditioner. I'm not seeing nothing out there. Now, it's hazy out there. There's not much to see. So I'm just going to call it. I'm not wasting nobody's time here. I'm not going to do that. It's not fair. So I'm just going to call it because I'm not seeing anything out there. I'm not. We were just looking out there and we're not seeing nothing with the naked eye. So, like I said, I'm not wasting nobody's time here. So I'm going to end the stream and bring all the equipment in, which is a pain. So I just want to wish everybody a great night, great morning, wherever you are. Be well, be blessed, be safe, and have a great night. Unfortunately, dud.